This lecture is on Chapter 6, the bones and skeletal tissues. Let's start by talking about the functions of bones. Bones support the body and the soft organs, forming the framework of the body. Bones protect the brain, spinal cord, and the vital organs, such as the heart and lungs. Bones provide movement by acting as levers for muscle action. When a skeletal muscle contracts, it pulls on the bone and moves the skeleton. Bones also store minerals such as calcium and phosphorus. Calcium is the most abundant mineral in the body. The bones also store growth factors, which increase the length of the long bones. Blood cell formation, or hematopoiesis, occurs in red bone marrow cavities, and triglycerides are stored as energy in the yellow bone marrow cavities. There are two main groups of bones in the skeleton by location: the axial skeleton and the appendicular skeleton. The axial skeleton consists of the head and vertebral column and thoracic cage. The appendicular skeleton consists of the bones of the upper and lower limbs and the girdles that support them, such as the shoulder girdle and hip girdle. Skeletal cartilages help to support the bones. They are avascular and non-innervated, and if they are injured, their recovery is very slow. But alas, they are very important because not only do they support the bone and prevent friction, but they also serve as a foundation for bone formation. All skeletal cartilages contain an extracellular matrix of dense jelly-like ground substance along with its fibers. Cartilage is surrounded by a dense irregular connective tissue girdle. This is called perichondrium, and it contains the blood vessels that do deliver nutrients to the chondrocytes to keep them alive. There are three types of skeletal cartilage: hyaline, elastic, and fibrocartilage. Hyaline cartilage provides support, flexibility, and resilience. It is the most abundant type of cartilage. When we talk about most of the cartilage in this chapter, we'll be referring to hyaline cartilage. Elastic cartilage is similar to hyaline cartilage, but it contains elastic fibers. This allows it to bend. You find elastic cartilage in the earlobes and also the epiglottis. Fibrocartilage will contain collagen fibers that have great tensile strength, and they'll be arranged in parallel arrangement so that it kind of forms threads. I think of the fibrocartilage as acting like a rubber tire. It has to support a lot of pressure. The blue is the hyaline cartilage. You see it's at the tip of the nose, it's the costal cartilage of the ribs, it's the articular cartilage that forms the ends of the long bones. It is also found in the respiratory tract. The elastic cartilage is shown in green, and it's found in the earlobes and the epiglottis. And the fibrocartilages, being like those dense rubber tires that have to withstand a lot of pressure, will be found in sites of compression, such as between the vertebrae, also the pubic symphysis, and even the meniscus of the knees. Bones are classified by their shape and also their texture. Let's talk about shape. There are long bones and short bones, flat bones and irregular bones. Long bones are longer than they are wide, and they are going to be found primarily in the upper and lower limbs. As you can see, the humerus, radius, ulna, metacarpals, and phalanges of the upper limbs. The femur, tibia, fibula, metatarsals, and then also the phalanges of the lower limbs. Short bones include cube-shaped bones found in the wrist bones and ankle bones, as well as sesamoid bones such as the patella. A sesamoid bone is a special type of bone that grows within a ligament. flat bones are thin, flat, and slightly curved. They are strong as a curve or an arch will distribute weight evenly along the surface. And so we find flat bones in the sternum and ribs and most of the skull bones. So as you can see, the flat bones have an important job to play. They protect the heart and lungs and the brain. Irregular bones have complicated shapes. So they're just kind of put in this category. And the vertebrae, scapula, mandible, and pelvis are all considered irregular bones. Sometimes you will see the scapula considered a flat bone as well. This illustration shows the long bone of the humerus in figure A. Figure B is an irregular bone. This would be a lumbar vertebra. Figure C is the sternum, a flat bone. And figure D is a short bone, the talus. Looking at the patella or kneecaps is an example of a sesamoid bone. Bones are very much alive, and they have lots of markings that will serve as sites of attachments for muscles, ligaments, and tendons, joint surfaces, and conduits for blood vessels and nerves. This graph shows, or table, shows different types of bone markings. And these help you when you are considering articular surfaces and sites of muscle and ligament attachment, as well as the conduits for nerves and blood vessels. As you can see, there are a lot of them. So we won't necessarily take the time to go through all of them. They're just there for your reference. All right. So next, bones are classified by their texture. There's compact bone and spongy bone, also known as cancellous bone. Compact bone has a dense outer layer, and spongy bone is a honeycomb of trabecula, usually found deep to compact bone. Spongy bone can be filled in with red or yellow bone marrow, and the spongy bone found in short, flat, or irregular bones is called diploe. Trabecula run along the lines of tension in a bone, and as you can see, the structure of the trabecula was the inspiration for the Eiffel Tower, because spongy bone is lightweight and airy, however very strong because it runs in those lines of tension. This helps to lighten the bone so that the weight is not too heavy as we're trying to move around. Let's look at the structure of a long bone. Remember, long bones are generally going to be found in the upper and lower limbs. They're going to be longer than they are wide. So a long bone will have a diaphysis or shaft and epiphyses, which will be the expanded ends of the diaphysis. The diaphysis has a compact bone collar, which surrounds a medullary cavity, usually filled with marrow. In adults, the medullary cavity will contain fat or yellow marrow. In infants, it will be red marrow. The epiphyses are the expanded ends of the diaphysis, and they have a spongy bone interior. The epiphyseal line is the remnant of a growth plate. The growth plate itself would be cartilage. The epiphyses also have articular cartilage on the joint surfaces. This is hyaline cartilage, and it prevents friction as the skeleton moves. The diaphysis is the long axis of the bone, and the epiphyses are the expanded ends of the diaphysis. You can see the diaphysis has the medullary cavity that's filled in with yellow marrow. This is an adult. And the proximal and distal epiphyses are named according to their attachment point. Proximal epiphysis will be closer to the point of attachment on the body, and the distal epiphysis will be further away. Both proximal and distal epiphysis have a spongy bone interior. Here we see an epiphyseal line, which is the remnant of that growth plate. So again, this is an adult. The articular cartilage lines the proximal and distal epiphysis and prevents friction as the skeleton moves. The periosteum is the outer fibrous membrane of the bone, and it is pictured here as a white colored structure because collagen fibers are white. There are two layers to the periosteum, the outer fibrous layer and an inner osteogenic layer. The outer fibrous layer of collagen forms protective covering for the bone beneath. The inner osteogenic layer helps form and remodel bone tissue. It includes osteoblasts, or bone-forming cells, osteoclasts, or bone-destroying cells, and osteogenic stem cells. The periosteum also allows the passage of nerve fibers, nutrient blood vessels, and lymphatic vessels to enter the bone via the nutrient foramina. Foramina means an opening. The interior of a long bone is lined by endosteum, and it is a delicate membrane, and it also contains osteoblasts and osteoclasts. Again, this shows the periosteum surrounding the perimeter, of the bone, osteo, and then the endosteum, endo within osteo, the bone, is found lining the medullary cavity in this illustration. In a short, irregular, and flat bone, the periosteum and endosteum are also found. Recall that the spongy bone is called diploe in flat bones. There will be bone marrow within the diploe, between the trabeculae of the diploe, and this bone marrow is generally red bone marrow in adults and also red bone marrow in infants. This illustration shows the flat bone of the skull with the outer compact bone layer and the inner compact bone layer. Sandwiched between the two compact bone layers, a spongy bone, also known as the diploe. Magnified is the trabecula of the diploe, and it will be filled with the red bone marrow. So flat bones are very strong. Again, the stress is going to be distributed evenly throughout the surface of this bone because of that arch. Let's look further at the red bone marrow location in the bone. So the red bone marrow cavities of adults will be found in the trabecular cavities of the heads of the femur and the humerus. So basically in the proximal epiphyses. That's what the head is of a long bone, the proximal end. Red bone marrow will also be found in the trabecular cavities of the diploe. Particularly the coxal bones or hip bones are a great place to harvest red marrow in an adult. The red marrow of newborn infants is going to be found in the medullary cavities of the long bones and all the spaces in the spongy bone. Now let's look at the microscopic anatomy of the bone. Everything we've just looked at prior to this was categorized under the gross anatomy, right? The structures that you can actually see with your eyes. With the microscopic anatomy, one would need a microscope in order to view these structures. So let's start with the cells of the bone. There are four major cells of the bone: osteogenic cells, which are the stem cells, osteoblasts, which are bone-forming cells, and here's the picture of the osteogenic stem cell and the osteoblast. The osteocytes are mature bone cells. The osteoclasts are cells that break down and resorb bone matrix. The mature osteocyte stems from the osteogenic stem cell. So it goes osteogenic stem cell to osteoblast to osteocyte. That's the lineage. However, the osteoclast, shown in figure D, is a different kind of cell. It is a modified macrophage, basically a modified white blood cell. And It is a very large cell with many nuclei and endomembrane systems because it's making a lot of enzymes that need to reabsorb bony tissue. Osteoclasts are very important in remodeling the bone as well as maintaining a constant supply of blood calcium levels. The undulating part that you see on the left side of the osteoclast is the end in which it will attach to the bone. Compact bone microscopic anatomy is made up of the Haversian system or the osteon. This is the structural unit of the compact bone. The osteon contains lamella. Lamella means sheet, like laminated. And these sheets are going to occur in a column-like pattern because, again, having an archway, a circular formation without any angles, makes for a stronger material. And so the lamellae are column-like matrix tubes that are weight-bearing, and they will surround the central canal. And the central canal will contain blood vessels and nerves. Remember, the bone is very much alive. The lamellae can surround the entire bone as circumferential lamellae, or it can also be found lying between osteons, and that's called interstitial lamella. So basically, lamella are the sheets of bony tissue that form the osteons and all the structures that support them. And the central canal is located in the center of the osteon, and this is where blood vessels and nerves will travel throughout this otherwise impenetrable matrix. This illustration shows the lamella. You can count 3 lamella in this picture. And they are going to be bound together by collagen fibers. Because remember, collagen is the most abundant protein in the body, and it binds and supports all of the tissues and organs in our body. The center of the osteon can be called the central canal. And here we see the arteries and veins as well as a nerve fiber passing through. The twisting force seen at the bottom of this illustration, the collagen fibers are going to help resist that twisting force. Sometimes you will see them referred to as the twister resistor. Other features of the osteon include perforating or Folkman's canals. These run at right angles to the central canal and allow for the blood vessels and nerves to pass from the nutrient foramina of the periosteum all the way through the bony tissue matrix into the endosteum or the inner trabecula or the medullary cavity, whatever is located deepest in the bone. Lacuna are going to be small cavities that contain the mature osteocytes, those mature stem bone cells, because the osteocytes will be secreting the bony matrix around them, and so they basically will trap themselves in these lacuna. The osteocytes, being very much alive, need to communicate with one another, and they do these through small canals called canaliculi. These are hair-like canals that connect lacuna to each other and to the central canal. So here's the big picture. On the outside of the bone collar is the periosteum, and interior to that will be the circumferential lamellae. These are the lamellae that will surround the entire bone collar. Deep to the circumferential lamella will be the osteons, and the osteons will be composed of their own lamella forming these columns, and in the center of those columns will be the central canal or the Haversian canal that allow for the passage of blood vessels and nerves. Between the osteons will be lamellae called interstitial lamella. Interstitial means between. The Folkman's canals are pictured running at right angles to the central canals, and you can see that they run from the periosteum all the way through the bony matrix of this bone collar and then end up deep in the spongy bone on the interior. The lacuna are going to be the spaces in which the mature osteocytes are confined, and the canaliculi will allow for communication between those osteocytes. Also, it will join them to the central canals so that they can get their continuous blood supply. This picture illustrates the lacuna and the central canal very nicely. And one thing to make note of is that the lacuna are located on the boundaries of the lamella, because remember, the osteocytes are forming the bony matrix around themselves. And so it makes sense that they would be building the lamella around themselves. Now let's talk a little bit about the microscopic anatomy of spongy bone. So there will still be the osteogenic stem cells. There will be osteoblasts, osteocytes, and osteoclasts. The trabeculae, as mentioned before, are going to run along lines of stress, and there's not going to be an osteon. There will be lamella, though, but the lamella are irregularly arranged. And there will be capillaries running throughout the endosteum to supply nutrients. What this slide is showing is the chemical composition of the bone. So remember, with connective tissue, you usually have two parts. You have the cellular part and the fibrous part. In the case of bone, the fibrous part can bind to inorganic materials. And so anatomists will usually divide bony tissue into organic and inorganic materials. When we look at anything that is organic, it is going to be forming carbon and hydrogen bonds, or it could also include the actual living cell. So here we see that osteogenic cells, osteoblasts, osteocytes, and osteoclasts are all included in the organic matrix. The osteoid is going to be the organic bone matrix secreted by osteoblasts. And this will include proteins, which will, of course, have those carbon and hydrogen bonds. So the ground substance will have proteoglycans, proteins and sugars, and then glycoproteins, which is another arrangement of proteins and sugars. And of course, collagen fiber. The inorganic composition lacks the carbon and hydrogen bonds, and these are going to be the mineral salts called hydroxyapatites. This makes up 65% of the bone by mass, and it's mainly going to be calcium phosphate crystals. This is what's responsible for the hardness and the resistance to compression that the bone affords us. The calcium and phosphate will be absorbed from the blood and placed into the bone by the osteoblasts. Once it reaches a certain ratio, it will crystallize. Kind of like once water reaches a certain temperature, it will form ice. It is important that bone development is regulated by hormones and also, just fetal development. And so the bone formation will begin in the second month of fetal development, and it's regulated at certain critical points. It will even be to the detriment of the mother if she is lacking in those nutrients. The body will still take them, whatever is in that body, and will give it to those fetuses. And so sometimes pregnant women might start noticing, cavities and stuff forming in their teeth because they're losing that calcium. So bone formation is very important, and that calcium and phosphate hydroxyapatite crystal has to be laid down and crystallized. And this continues until adulthood, and then bone remodeling will take over through the rest of one's life. And that's called postnatal bone growth and bone remodeling and repair. There are two main types of ossification. Ossification is the actual formation of the hydroxyapatite crystals once they are laid down in that certain ratio. The first kind is called intramembranous ossification, and membrane bone will develop from a fibrous membrane, and we'll find these in the flat bones, such as the clavicles, which are your collarbones, your cranial bones, your sternum, etc. The second kind of ossification is called endochondral ossification, and this is the ossification that occurs on hyaline cartilage skeletal model. So this will form most of the rest of the skeleton. So you'll basically see intramembranous ossification in the face, as well as in the thoracic cavity, clavicles, and then endochondral ossification you'll basically see everywhere else. So endochondral ossification uses the hyaline cartilage models, and it requires the breakdown of hyaline cartilage prior to ossification. The intramembranous bones are forming in the skull of this fetus here, and then you can see the endochondral bones are forming in the upper and the lower limbs. And it is regulated and should be occurring at a specific stage each week during fetal development. At birth, you can see that the bone collar has been formed in a long bone, and there's a medullary cavity and a nutrient foramina allowing for the passage of blood into that medullary cavity, which it will be filled with red bone marrow. And then the epiphyses will start to be ossified, and the articular cartilage will form, as will what's called the epiphyseal plate. The epiphyseal plate is a site of long bone growth that will not ossify completely until puberty ends and adulthood is reached. The growth in length, the longitudinal bone growth mentioned, is called interstitial or longitudinal bone growth. This increases the length of long bone and is primarily influenced by growth hormone. Appositional growth is going to be the increase in the thickness of the bone growth, and it will remodel all of the bone's surfaces so that as the bone widens, the medullary cavity will also widen. As the epiphyseal plate is growing, there are four important functional zones: a proliferation or growth zone, a hypertrophic zone, which is where the cartilage cells will die, and then calcification, which is where we're starting to lay down the calcium, and then finally ossification, where it crystallizes. So number one, the proliferation zone occurs where cartilage cells undergo mitosis, and they are pushing the bone epiphyses away from each other as they undergo mitosis. In the hypertrophic zone, the older cartilage cells will enlarge, and eventually their cavities will break open and the cartilage cells will die and the matrix will become calcified. In the ossification zone, the new bone formation is occurring, and the hydroxyapatite minerals will form as they are laid down in their appropriate ratio. Bone growth that is going to increase in the length of the bone is that longitudinal growth, and then remember the appositional growth is going to be part of the remodeling process. And this will help to ensure that the medullary cavity continues to widen as the bone widens. And we want to maintain a steady thickness of the bone collar. We don't want the bone to become too thick. We don't want it to become too thin. You know, it needs to be regulated. Also, these spurs that you can see on the interior of the medullary cavity will be shaved down by those osteoclasts. So as the bone grows in length, it also will grow in width appropriately. Here's some of the hormonal regulation of bone growth. Growth hormone will stimulate the epiphyseal plate activity, increasing the length of the long bones. Thyroid hormone helps to modulate the activity of growth hormone, keeping it in check. And then there are testosterones and estrogens that occur at puberty. And they will do two things. They will promote adolescent growth spurts, and then they will end the growth by inducing the epiphyseal plate closure. So not only do they encourage bone growth, but they also will encourage the end of bone growth. Bone deposit occurs where bone is injured or added strength is needed. And this requires a diet rich in protein, vitamin C, D, and A, calcium, phosphorus, magnesium, and manganese. During bone deposit, the sites of new matrix deposit, so that, collagen being laid down first and then hydroxyapatite, will be revealed by the osteoid seam. So this will be the unmineralized band of matrix, those collagen fibers that are being laid down. And then where the calcium and phosphate is being laid is called the calcification front. And it's the abrupt transition zone between the osteoid seam and the older mineralized bone. Did you know that about every 10 years you have a new skeleton? Unfortunately, though, a lot of us are lacking a good diet and a lot of us are lacking a regular exercise regime. So our skeleton gets replaced every 10 years, but it's not always replaced by a stronger skeleton. Usually the opposite is true. When bone is resorbed, the osteoclasts are doing this, and they are secreting lysosomal enzymes, which will digest the organic matrix, and then acids, which will help to convert calcium salts into soluble forms. The dissolved matrix is then transcytosed or absorbed across the osteoclast. It enters the interstitial fluid and then goes into the bloodstream. So not only do osteoclasts help to remodel bone and maintain a nice shape, but they maintain blood calcium levels as well. So as I mentioned with fetal development, the mother skeleton is going to sacrifice enough calcium so that that fetus can grow at the predetermined, rate. And our bodies, whether pregnant or not, will always be reabsorbing calcium to maintain a calcium range homeostasis. And so if the diet is lacking and regular exercise is lacking, the skeleton can get weaker over time. So what controls the continuing remodeling of bone? The hormonal mechanisms that maintain calcium homeostasis in the blood and mechanical and gravitational forces, also known as Wolff's Law. So right here, these two things are going to emphasize the importance of a proper diet and regular exercise, because you want to make sure that you have enough calcium in your blood so that you don't have to lose it from your skeleton. And you also want to make sure that you're putting enough mechanical and gravitational forces on Wolff's Law to encourage bone remodeling and keep your bone density up. Let's look at calcium and what it is necessary for. Why do we need a calcium homeostasis of our blood? Well, it's because calcium is necessary for the transmission of nerve impulses, muscle contraction, blood coagulation, the secretion by glands and nerve cells, and cellular division. The parathyroid glands are glands that are located just posterior to the thyroid gland. They're actually like on the thyroid gland, but on the dorsal side. And if the thyroid is removed in its entirety and hormone therapy is not done to maintain parathyroid hormone, all of these processes mentioned on this slide will crash, and that can lead to death in the patient. So the hormonal control of blood calcium levels will be primarily controlled by the parathyroid hormone. And this is what stimulates the release of parathyroid hormone. If there is a drop in blood calcium levels, then the parathyroid gland will release parathyroid hormone. Parathyroid hormone will then stimulate osteoclasts to degrade the bone matrix and release calcium into the blood. And this will increase blood calcium levels to the homeostasis regulation point. And so here's that homeostasis regulation point, the set point as we call it. And the range is 9 to 11 milligrams per 100 milliliters of blood. And you'll see this sometimes as like 8.9 to 11.1, sometimes, the book will get real specific about it. But this figure is just 9 to 11 milligrams per 100 mils. And as the calcium levels drop below that 9 milligrams, the parathyroid hormone will release from the parathyroid glands, and it will cause the parathyroid hormone to increase in the blood, stimulating the osteoclast to degrade the bone matrix and release calcium into the blood, raising it back to its set point. There's also another hormone called calcitonin, and this is a lesser effect because this only occurs when there is an increase in blood calcium levels or after mechanical force from like exercise. And so what calcitonin does is it's going to respond to the increase in blood calcium levels, and the thyroid will release calcitonin. So it's not parathyroid glands, but it's actually cells in the thyroid itself, which will release calcitonin. And this will cause the osteoblast to take the calcium out of the blood and deposit the calcium salts into the bone. And this will drop blood calcium levels back down to the set point. The Wolff's Law states that a bone grows or remodels in response to the forces or demands placed upon it. Several observations that support Wolff's Law. The first is handedness, right or left-handed people. This results in the bone of one upper limb being thicker and stronger than the other. We see curved bones are thickest where they are most likely to buckle from all the compression forces. Trabeculae will form along lines of stress, and large bony projections occur where heavy active muscles attach. So the mechanical forces placed upon the bone can make the bone stronger. It takes a lot of pressure to break a bone. Correct me if I'm wrong, but I know that the femur, it will take over 2,000 pounds of pressure to break the femur. And that's why femoral fractures usually bad news, right? You've got hit by a car or something like that. This illustration shows the x-ray films of the playing and non-playing arms of a professional tennis player. So without even reading which one was the playing arm, you can see that it's the right illustration, and the non-playing arm is the left illustration. I used to work at a racket and swim club when I was in high school. I was a lifeguard, and I did notice that like tennis pros had notably larger dominant arms than their non-dominant arms. So if they were a right-handed tennis player, which most were, they had a larger right arm. As mentioned earlier, it does take a lot of pressure to break a bone, but alas, it happens, and bones do fracture. And so luckily, the bone is very much alive and has a lot of blood and nerves, and so it can heal. So in the stages of healing, the first stage is the formation of a hematoma, which is a blood clot. The site becomes swollen, painful, and inflamed. And this is like a telltale sign of what bone has been broken in what area to a lot of medical professionals, especially, if it's not a fracture that's open, where the bone is sticking through the skin. Using the hematoma location, you can still pinpoint the site of injury because of that swelling and pain and all that. So this is step one, the hematoma formation. And inflammation, if you remember, in tissue healing is very important because as it swells, it's bringing tissue fluid into the area, which is helping to bring in white blood cells, cleaning up bacteria, and it's also bringing in a lot of nutrients so that the tissue can start to heal. So, ouch. The second stage is the fibrocartilaginous callus. So first and foremost, this is kind of like the granulation and proliferation stage of tissue healing. So phagocytic cells are going to clear the debris, and the osteoblast will begin forming spongy bone within 1 week. So this is going to be kind of like the granulation tissue that's analogous to it. The fibroblast will then secrete collagen fibers to connect the bone ends, And the mass of repair tissue is now called the fibrocartilaginous callus. This is what it looks like. We're starting to patch it up, and the blood vessels, that granulation tissue starting to grow back through the new membranes and collagen being laid down. So it's important to set the bone, as you all know, because you want the bone to be able to heal correctly. The third stage is the bony callus formation, and new trabecula will form a bony or hard callus. So spongy bone will be laid down first, and bony callus formation will continue until a firm union is formed between the two ends of the bones, proximal and distal end of the break, and this takes up to 2 months. 6 to 8 weeks is usually when you're in a cast or splint. So this is showing that bony callus formation occurring. It's just great that the bones can do this. Thank goodness, right? And then finally, bone remodeling occurs. So this will be in response to the mechanical stressors over several months, and eventually the final structure can resemble the original. And some folks will report pain, at the site of the break for years, maybe indefinitely after. And a lot of times, you may have experienced this too, but the patients that I talk to who've continued to have pain usually have like the screws, as you can see in the picture of the broken knee there, the broken leg. And that will, a lot of times, like expand and contract with weather changes and stuff like that and cause pain. Because remember, the bone is going to be full of nerves and blood, so it's very sensitive. So here's a healed fracture. And here it is all together. Step 1, a hematoma forms. Step 2, a fibrocartilaginous callus forms. Step 3, a bony callus forms. And step 4, bone remodeling occurs. During development, homeostatic imbalances can occur. So let's look at osteomalacia, also known as rickets. So what's happening here is that calcium salts are not being deposited correctly, and this is usually due to a lack of vitamin D or insufficient dietary calcium. So this is one of the first childhood diseases that was linked to nutritional deficiencies. Osteoporosis is the loss of bone mass as one ages, and there's still a lot of studies on its causes as well as its treatment. And the spongy bone of the spine and the neck of the femur will become most susceptible to the fracture. So risk factors are a lack of estrogen, calcium or vitamin D, a petite body form, immobility, low levels of thyroid stimulating hormone, and the presence of diabetes. Osteoporosis is more likely to affect women and men because after menopause, the women will drastically lose their estrogen, whereas estrogen levels stay steady, if not increase, in men as they age. This illustration shows a normal bone and an osteoporotic bone. So like a soft, brittle bone. And the neck of the femur is highlighted here because this is one of the primary sites. It's mentioned in the slide before that the osteoporosis affects, as is the spongy bone located within the body, the vertebra. To help treat and prevent osteoporosis, calcium, vitamin D, fluoride supplements, weight-bearing exercise throughout life, hormone replacement therapy can slow bone loss, and then some drugs such as Fosamax, SCRM, statins increase bone mineral density. Another type of homeostatic imbalance is called Paget's disease. This is the excessive and haphazard bone formation and breakdown, usually in the spine, pelvis, femur, or skull. Pagetic bone has a very high ratio of spongy to compact bone, as well as reduced mineralization. It could be viral, there's an unknown cause, and treatment will include calcitonin as well as biphosphonates. To end with, the developmental aspects of bones, recall that embryonic skeleton ossifies predictably, so fetal age is easily determined from x-rays or sonograms, and of course hormonal levels in the mother's blood or amniotic fluid. And at birth, most long bones will be well ossified, as we saw the bone collar formation had already pretty much occurred, except the epiphyses are still growing, and that's where that epiphyseal growth plate will be. That will increase the length of the long bones until the end of adolescence. So here's a beautiful picture. You can see the development of the fetal bones. Nearly all bones are completely ossified by the age of 25. Bone mass will decrease with age beginning in the 4th decade, so that's going to be in your 30s. And the rate of loss will be determined by genetics and environmental factors. And in old age, bone reabsorption will predominate bone deposit. And that's the end of the chapter. Thank you for listening. This is the Lover's Embrace, I believe, Pompeii, when Mount Vesuvius erupted, and the city of Pompeii was covered in ash. So it's a very sad but also very sweet picture. Thanks again.